Today we'll review Chapter 7 on Resonant Pulse Inverter. Resonant Pulse Inverters are very common in a situation, especially for high frequency applications. If you have a normal inverter like pulse width modulation, we're trying to obtain a sinusoidal output voltage as much as possible. But with the resonant pulse inverters, you create an LC resonance circuit, and ideally, if there is a LNC circuit without any resistance, the oscillation will continue forever, and the waveform you expect the sinusoidal waveform. But in real life, that there will be some resistance in the circuit. There will be a resonant oscillation, but it's a damped resonant oscillation that will not be perfectly sinusoidal, but close to the sinusoidal. That's why the resonant inverter are very often used for high frequency application like induction heating, because the frequency depends on the LC value there. And we are going to review that. That's the one. And let me go to the next one. And if you go to the next one, this is this resonant oscillation circuit. You have a thyristor here. You got a thyristor here, as you know that. And then one of them is all. There will be RLC circuit. There will be resonant circuit there. The question asked, in order to sustain an oscillation, the RLC should be such that it forms a undamped undamped the circuit. It cannot be critically damped. It can be overdamped, but it basically should be underdamped circuit, so that resonant oscillation continue. And then normally that there should be the resistance of the circuit should be low, and that's the idea. Now the answer is like underdamped natural frequency. And now this one, the resonant frequency of this circuit, if you look through the resonant frequency of this circuit, you got a R, L, and R, L, and C circuit you got. If you look through the resonant frequency, you can calculate it out. Resonant frequency of this circuit, if you look through that, one of the basic circuit was derived. It was derived in that, one of the equations, you can find it out. The resonant frequency will depend on these, is in equation 7.4. You're going to find that it will depend on the R, depend on the L, even the C, that is, all of them will depend on. The resonant frequency depends on all of them. Now, the resonant frequency, what will happen, increasing the value of R, will cause the resonant frequency to decrease. Obviously, if you look through that equation, that if you're going to increase that R, the frequency will be decreased that. Increasing the R will decrease the resonant frequency of the circuit. If you look to the equation, then you're going to find that increasing that R will reduce the resonant frequency. And the coupled inductors, now in this particular case, this inductor L1 and L2 coupled so that they share that the current as much as possible under transient condition. The function of the coupled inductor is to ensure the one switching device can conduct at the same time. What will happen then, if one of them is conducting, then there will be a positive voltage between top to the down, and then similarly that the other one will be also positive and negative. You can see that anode of the devices will be the anode of that devices will be the anode of this device will be the negative. As a result, that device has to turn off. That means one will ensure that only one device can conduct. The function of is to ensure that only one switching device conduct at the same time. That's the answer. Now, if you look through the next one, effective capacitance. This one, if you look through that, this is the half-bridge capacitor. With the capacitor, the C1 and C2, the C1 and C2, it is like this. It's divide the voltage, the Vs, into two. Like if this is a 200 volts there, it will be 100 and 100, or if there is 150 and 50. That capacitor acts like this, the energy storage or voltage divider. That means that if this is a parallel, that capacitors will be the sum of the two. It will be C1 and C2. And remember that if the capacitors are in series, they are like they behave like this. They are like a parallel combination. If they are series, then it will be like other way. Okay, that's C1 plus C2. The resonant frequency of this circuit, you can find out there is one of the examples. I encourage you to do this calculation. This is one of the examples is coming up. Like example of this one is coming in example 17.2. I encourage you to do all these workout examples in the book. There are some videos there. You can find out the equation 721 tells you how what will be the, you C1 is given, C2 is given, L and R is given there, and you should be able to calculate out the numbers give you that. I encourage you that you review the videos for the worked out examples. There are Mathkit files. You don't have to learn anything about it. You just run those files and change the values. You can see this. You can calculate it out. This is the full bridge inverter, and if you got a full bridge inverter, that what is happening that if you have a 1 and 2 conduct, 1 and 2 conduct, you have a resonant pulse of the circuit like this, and then on the other hand, when the 3 and 4 conduct, as far as the output is concerned, that this if it is a concern that that will be the other way. Now, what is the question of supply? The supply current. You're asking for the current from the supply. You're asking for the current from supply. What will happen the first half cycle? The current, if you look to the current from the goes the first cycle, and the other one also this goes from 3 and 4. 3 and 4, it will be also another pulse there. The current is always a DC. What is a DC? If you put an emitter, or look through an oscilloscope, the current is always positive flowing from, say, A to B, and it doesn't go the other direction. That is the unidirectional current. This will be pulsating. That means the supply current of the full bridge inverter is a pulsating DC current. Okay? That's not a square wave. It will be pulsating. It will be pulsating. It will go up and down, but it's a pulsating. The DC. DC means is unidirectional, the current there. If you look to the resonant frequency, they ask load current of the resonant inverter. Now, what is the load current? If you look to the resonant current here, it's another story there. If you do 1 and 2, the current will be like this. But if the other and 2, it will be the other way. The current will go the other way in opposite direction. That means that the current will not be sinusoidal, but sort of a pulsating sinusoid will go up and down there. It will be up AC alternating current. The current will go, if you look to this load, the current will go once in one direction, other times the other direction. That means that will be a pulsating AC current, not a DC current. Resonant oscillation to continue. For resonant oscillation to continue, what will happen there? The ideal device, this oscillation continue to for how many degrees? And that continue, we'll look at that. If you go first, one will continue to 1 and 1, and then the other one will continue to this diode, and there are the other one. There are four possible. There are 4 devices that will be each one of the continue. One of them is continuous to that, and then the other one will continue from the freewheeling diode. The current can continue, and then the rest of the other one. There are 4 of them. This will be the oscillation can continue 360 to 60 degree. If there is an ideal diode, the resonant oscillation for this 360 degrees continuously conducting, it's an ideal device. If this is an ideal device, there will be some the discontinuity between one device to the other devices. But if there is an ideal device, that will be a continuously signed, and it's pretty much without pretty much sinusoidal, pretty much close to the sinusoidal, and continue to that oscillation to continue. And this is what is happening. That if you look to this figure, let me show you the figure like a 7.5. If you look to the figure 7.5, you're going to see that. Now, this is the answer. Now, conduction of each device is what is going to conduction of has devices you're going to conduct. If you got this one, if there is the ideal devices, then ideal characteristic, 1 and 2 will continue 180 degree, 3 and 4 180 degree. That means each device 180 degree of the output cycle. Whatever the output cycle will be, as long as it's not a discontinuous, it will be 180 degree of the output cycle. Now, conduction of each transistor device. What will happen in each transistor device? This will be, there are 4 of them, there are 360, it will be 90 degree each of them. That the ideal, assuming that there is no delay time, there is no nothing a turn of time, each the conductor will conduct for 90 degree. That's the simple answer. Now, conduction of each transistor, we mentioned that 90 degree. Let's go further. The output voltage. If you look to the output voltage, the output voltage can be varied. If you can vary that by shortening the resonance, if you don't let the oscillation to continue 360, if you don't continue the oscillation To continue beyond that, like if you look for the figure 7-8, 7-8, you can make it like 7-9. In figure 7-9, you can extend it or shorten that oscillation. If you do that, you should be able to vary the output voltage. The output voltage can be varied by shortening the resonant oscillation. If you don't shorten it, it will be the maximum, or otherwise you can vary the output voltage. Series resonant inverter, if you got a series resonant inverter, what you're doing now, you are having a form a series circuit, RLC circuit. If you look to the RLC circuit, then what will happen that if you got the output voltage of the resonant circuit, if you look to the figure 713, the frequency of the resonant circuit is given A and B. You say that the output voltage decreases with the increase of the Q factor. If you increase the Q factor, the output voltage will decrease. Decrease with the Q quality factor of the output voltage. This is in figure. I believe it's in figure 712. You can see that if you increase the quality factor, the output is going to decrease. And that is this is the output voltage. This is an equation. You can see 735. You can look for that. Now, the maximum output voltage, obviously the maximum will be at the resonant frequency. The maximum output voltage resonant inverter always works at that resonant frequency, because if you have the resonant frequency, the impedance of the inductor, impedance of the impedance of the capacitor, they cancel each other at the resonant frequency. Well, you can say that J omega L is equal to 1 by J omega C. As a result, there is no only impedance, you have the resistance R there. As a result, the maximum current you can flow through there. What is the maximum current? Peak of the supply voltage, or the DC is a normal DC there, divided by R. That will be the peak one there. The maximum output voltage occurs at the resonant frequency. The frequency higher than the resonant operating frequency at the higher than the resonant frequency, and that's the one. The maximum output occurs at the operating frequency higher than the resonant frequency. That's the, like you can see, that is the one of that one. Slightly for that. This is slightly offer that. The parallel resonant inverter, the output voltage parallel resonant inverter, and if you look to that, the figure, if you look to the figure 13, you can see that it's an opposite. The Q factor, the increases with the increase of the quality factor. If you have the quality factor increases, the output voltage increases. The maximum output voltage always, of course, offers the resonant frequency. And the parallel resonant inverter, the parallel resonant inverter, if you look to the parallel resonant inverter, you can see that it's skewed there. The decrease with increase the quality factor. If you increase the quality factor, that this output voltage decreases. The maximum becomes at 1 somewhere, not at the resonant frequency, at that other than higher than the frequency. And remember that the ratio, that U is the diagram, is the ratio of the frequency to the resonant frequency. The series parallel resonant inverter, the maximum output voltage always offers as the resonant frequency. Whatever the resonant frequency is, the maximum is going to happen to that one. Parallel resonant inverter, that particular case, that if you look through this diagram, if you look through this equivalent circuit of this one, that becomes this decrease of the quality factor of that. This one equation becomes 747. That becomes a 443. That is similar to the equation 712. Decreases the quality factor of this circuit. The maximum output voltage, again, it happens that it doesn't matter whatever this one. Adjustable output voltage. You can adjust it. The output voltage will be adjusted by controlling the gate of the switching circuit. It's true. If you adjust the gate voltage and the gate signals, the lower than that, not to go oscillation from 180 degree, we can do once could vary the output voltage. This is true. Zero switching up examples. There are two types of zero switching. It could be M type, could be A type, L type, but you could be implemented both M and N type, both of them, M type and L type, both is a focus. Now, if you look to the zero type switching, current means that in this case the waveform type zero, the current becomes a zero. When the current full wave type zero current switches, the current falls to zero. That's the time you turn it on. And what is happening if you do the zero switching? the voltage, whatever the voltage, the current is zero, the power distribution across the switch becomes zero. That's why zero switching is very useful for them. Hulu have to have zero current switching, and will switch the device when the current falls to zero. And then also zero voltage switching of type with the zero voltage. In this case, you look at that configuration, the voltage becomes zero. That time you switch the device. So the current could be different, but the voltage is zero, but the power dissipation across the device becomes low. And this is the one is the output voltage of that. You got you got a number of like a tank service you have, and you got one device that you got to try going to you increase the three-phase voltages from the resonant circuit. The period of the waveform will be both even numbers of the the period. Like if you go to this one of the diagram you have on this one is called this. You can see that the diagram. I'm trying to find it out. This is this tank one. You have that. And if you look to the equation 766, and then the output voltage, of that tank inverter, you can have that inverter of that. It's like so this is the 735. If you go to 735, equation 768, that is this. It could be even and odd numbers of the period. It could be even and odd number of the period. The both even and odd multiple of the tech period output will be there. There's no limit to that. I think that's the end of that the chapter. I will encourage you to review that the videos of the chapters, and also particularly that review the MathCAD files. You can run them through this the desktop. It's very simple, and it's very simple. There is a video to how to use them. I think that's the end of that one. I'm trying to get back to my